In this video, we're going to talk about continuous growth, and it's the idea that if you were able to compound constantly, just continue to compound as much as possible, what's going to happen? So in this example, they took a dollar investment, they looked at the annual, quarterly, monthly, daily, and then they started breaking it down by hour, by minute, by second. And as you can see, it stops kind of changing all that much, right? From hour to minute to second, right? I mean, the changes aren't that big. And what that means is that it's going to kind of cap out. They're not going to really keep jumping in investment, even if you did half seconds or quarter seconds, right? The idea is it taps out a little bit. And that's interesting when you think about it. What they actually end up kind of converging to is an actual number called E. And E is approximately 2.718282, and it keeps going forever, just like pi. Okay, it's an irrational number. It goes on forever, but it is an actual number. And what's amazing is E occurs in nature. It's actually something that we see modeled in nature, especially when it comes to certain types of growth models like we're talking about here. Okay, so let's talk about how it would look in terms of compound interest, since it's actually possible to calculate a number where if you keep compounding, we're actually able to create a special formula. Now, really quick, we're going to be introducing a new exponential, e to the x. And e is actually on every scientific calculator. Typically, you have to hit the shift button or the second button, whichever it's called on your calculator. And it's usually above a button that's LN. Okay. You usually see it above the button that's labeled LN. And that's an E button. Some calculators even have a separate button just for the number E. Like the button that I'm referring to is usually like E raised to the X. But yeah, it's actually on your calculator. Take a second, locate it. And if you have any trouble, send me a message, a picture of your calculator, and I'll be more than happy to help you out. So the formula we'll use for continuous growth is f of x equals a. So this is what we're investing. But instead of doing that 1 plus 1 over k or 1 plus r over k, we're going to replace that with e to the r times x. Okay, where x is, oh, interesting. They didn't actually define that, but x is our t. It's our how much the time that we're looking at. Let's put that there. Okay, so let's go ahead and look at an example of this. So a great example is often in chemistry when we're talking about like chemical reactions, which can happen very rapidly. Continuous growth kind of helps with this, or continuous decay if you're talking about a decay in value. Okay, so in this particular example, radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay in 3 days? Okay, so we're going to use our formula. I'm going to just rewrite it. F of x equals a e to the rx. So a in this is the amount we're starting with, which is 100 milligrams. E is a number, so that's done. The rate is the decay. Now, the decay means that we're going to throw a negative in there. Okay, that's going to make this a negative 0.173. And then the time in this case is 3 days. So 3 in for x. So we're going to plug this into our calculator. And again, find your E button to enter this into it. I'm going to go ahead and plug this in really quick. E to the negative 0.173 times 3. Also, make sure you're using your negative button, not the minus button. There's a difference. 59.51 is what I am getting. And this would be milligrams. So that's how much is going to actually be left after 3 days. So almost half of it's gone, not quite, but almost half of it is gone in 3 days. That's amazing, right? That's how rapidly this thing is decaying. Okay, let's look at another example. This time, let's look at an investment. So $1,000 invested into an account earning 10% compounding continuously. Find out how much is left after 1 year. So we kind of saw this earlier when they did the $1,000 invested at the different rates. And based on what we saw, it really shouldn't be a huge difference from the daily. But let's see. So 10% is our R, 1 year is our time. Plugging that in, we get 1105.17, which is very close to the daily amount that we saw previously. So that means really there's not a huge difference on the $1,000 when you're investing for just a year. There's probably bigger differences in larger money amounts for longer periods of time, but it isn't a huge difference for daily in that case. But that's how the formula works. And as you can see, it's actually a little less complicated than the compounding continuously formula from the previous video.